start coming up with a more kind of methodical way for us to find the derivative so that I'm not having to do everything from scratch by evaluating these limits. I'd like to see whether there are patterns that exist amongst kind of like classes of function. And we started to see that a little bit last time, right? So for example, here are some functions. F of x equals 3, g of x equals -2, h of x equals pi, k of x equals 1 divided by the square root of 2. So here's some constant functions. And what are the derivatives here? What's f prime of x if f of x equals 3? It is 0. Okay? This function is not changing. Right? It's just always 3. Right? If this were a line, it's a horizontal line. It has a slope of 0. So its derivative is always 0. Okay? Remember that the derivative is measuring instantaneous rates of change. A constant of 3 is not changing. It's 3, and a little bit it's going to be 3 again. A little bit after that, it's still going to be 3. So 0 change. What about g prime of x? G of x is -2. Also 0. What about h prime of x? Well, also 0. And k prime of x?
0.
Also 0. All right, so no big surprise here, right? Constants aren't changing. Their derivative is going to be 0. So we could put that into a box, right? That seems to be like a general thing about constants. So we could say if f of x equals c, where c is a real number, then f prime of x equals 0. There it is using prime notation. Right? And that's a fact about all real numbers. Any constant, its derivative is 0. In Leibniz notation, we might say this. ddx of c equals 0. Remember this d over dx notation, right? This is an instantaneous change of c divided by an instantaneous change in x, right? This is the derivative of what's inside the parentheses. It's the same as a prime, just written a little bit differently. We want to be familiar with both notations. We saw another example too last time. We saw things like f of x equals 2x, or g of x equals -3x, or h of x equals 1/2 x. Or let's do k of x equals 6x minus 7. So here are another 4 functions. And what about f prime here? What's the derivative of 2x? 2. Why 2?
Well, does the d over dx, and then it just drops the x after. Just like if it was like x squared, you just get rid of it, just be 2x.
We don't know that yet, right?
Okay.
We're just thinking about, what do I know about the derivative? It measures a rate of change. A derivative is talking about the slope of the function at a point.
Yeah.
Right? So what is 2x is a straight line. What is the slope of it anywhere?
It's the same.
Yeah, straight lines always have the same slope, right? They're not curving or anything like that. So we always got the same slope. Right? So straight line, right? The slope here is the same as the slope here, is the same as the slope here. Curvy things are more interesting because their slopes are always changing. Okay? I'm different. But here, it's always the same. So the slope of 2x is 2. This is always 2. What about the slope of g? Yeah, -3. It's this coefficient on the x term. Right? What about h prime of x? H is 1/2 x, so h prime is 1/2. Right? Whatever that number is in front of the x, that's the derivative. What about k of x here? K of x is 6x minus 7. Just 6. All right, so k prime of x is 6, right? This minus 7 didn't bother it at all, right? Because all of this minus 7 does to the graph, right? 6x might look like this. There's 6x, it's a straight line. 6x minus 7 is the same line, it's just moved 7 down. And remember, where the derivative is doesn't matter. It's only how steep is it. That minus 7 isn't changing the steepness. Okay, so new rule, right? We've got this new pattern. I'd like to talk about something else. So if f of x equals cx, then f prime of x equals c. In fact, I have a little bit more than that, right? I have if f of x equals any line, f of x equals mx plus b, then f prime of x equals m. It's just whatever the slope is. And it didn't matter that I was adding another number. What is the derivative of that, by the way? What's the derivative of b? If b is a real number. And it's going to be a 2 or a 5. The derivative of 2 is 0. The derivative of 5 is 0, right? So the derivative of b, if b is a real number, is 0. So I wonder if this is true. I wonder if I add two functions together and I take their derivative, what do you suppose happens? Do you think it's complicated, or do you think something nice might happen? If something nice happens, what defines nice? What happened back here, right? Here I'm adding two functions together. Mx is a function and b is a function. And the derivative of mx is just the m, right? And the derivative of b is 0. So the derivative of mx is m, and the derivative of b is 0. So what about in general? What if I did any function plus another function that followed the pattern of that very simple function? What would happen? What would you want to happen if life were easy and not complicated?
We would just add them.
Yeah, right? Yeah. I want it to be f prime of x plus g prime of x. That's what I want to be the case. I just want to take the first one and then the second one. And I have an example of a whole class of functions where that's exactly what happens, right? If I take some number times x plus some number, I can take the derivative of the first one is m plus the derivative of the second one is 0. M plus 0 is m. Okay? So here's an entire class of functions where that works out exactly. So that's encouraging. I just wonder whether it's true in general. It is. Always true. Always true, which is great. Do we want to see a proof? I want to see you all, remain unconvinced. We demand more evidence, sir. All right. Well, what's it going to look like? It's going to look like the limit as h approaches 0 of f of x plus h plus g of x plus h. Okay? Here's what happens if I plug x plus h into everything. I'm going to subtract what happens if I don't have that little h in there. So minus f of x plus g of x. Right? F of x plus g of x. There it is by itself. And I'm going to divide by h. Now, this all seems very general. I don't even know what f is. I don't know what g is. I'm going to try to mush it around anyway. That's f of x plus h plus g of x plus h minus f of x minus g of x, right? This minus is going to distribute in. And it doesn't matter what order I add things in, so I can just kind of keep them all on one line. And I'm going to have an h on the bottom. Now, I don't know what f is, and I don't know what g is, so I don't know exactly what's happening with these functions, but I might as well put all of the f's together and all of the g's together, right? Because it doesn't matter what order I add or subtract in. Right? Addition is, it's called commutative and associative. Those are the properties that I'd be using that basically tell me that order doesn't matter. I can switch everything around however I want. So I put the f's together, I put the g's together, and now I'm starting to see something kind of similar. Right? F of x plus h minus f of x divided by h plus g of x plus h minus g of x divided by h. Right. These look super suspiciously familiar. If h is going to 0, what's happening here? That's just the definition of derivative. Right. This is exactly f prime. And if h is going to 0, then this over here is exactly g prime. So it is no matter what f and g are, if f and g are differentiable, if their derivatives exists, then you can just take them one term at a time. Awesome. As some ancient mathematician might say, quod erat demonstratum. Thus it is demonstrated. QED. That's what that stands for. Nobody does that anymore because it sounds pretentious and looks silly. What you will see sometimes, though, is people will put a little bit of ink here. They'll do this. They'll put a little black box down at the bottom of it to say, I'm done. There it is. I did everything. It's called a tombstone. Or sometimes it's called a Halmos, after a guy named Paul Halmos, who's a really recent mathematician. As in, like, he wrote an autobiography. You could go out and buy his book. I think he's dead now, but he wasn't 20 years ago, right? Really recent dude, named after him.